So until now, we've talked about how an object moves, but we've talked about it just in terms of a description of its position and velocity. Now, you and I both know that when we're walking through a crowd, if someone relatively lightweight bumps into us at 1 kilometer an hour, it feels very different than if someone who is more heavyset or has been working out bumps into us at the same speed. What's the difference? Same thing when we pull on a door to open it, a light door feels very different than a heavy door. Well, the difference is how much mass these objects have. So closely related to the notion of velocity is the notion of momentum and mass. And the relation is like this. If I have a velocity q1 dot, then there's a corresponding momentum p1, and then the relationship is given by the mass. So for a given velocity, say 1 kilometer an hour, if the mass is large, I will have a larger momentum. If the mass is small, I will have a smaller momentum. I put these ones here specifically to talk right now about a relationship between a one-dimensional system and both in terms of its velocity and its momentum. And the reason is that for one dimension, we can get away with just putting down a real number for the mass. For example, if I have just the elevator going up and down, it's sufficient to talk about how much mass in kilograms that elevator has. However, when we talk in general about multidimensional systems, then the relationship between the velocity and the momentum can no longer be expressed by a single real number for the mass. Instead, we're going to use the most possible general linear relationship between the velocity and the momentum. If the velocity is a d-dimensional vector, and same thing with p, the momentum is d-dimensional, then what's the most general relationship between, most general linear relationship between two d-dimensional vectors? That's right, it's going to be a matrix that has dimensions d by d. And this matrix M is going to be the mass. Now, what does this matrix look like? Well, let's talk about the case of the two elevators. Clearly, the inertia of one of these elevators is independent of the inertia for the other elevator. So how much inertia this one carries is separate than how much inertia this one carries. So if our representation of the two elevators is in terms of Q1 and Q2, so our velocities look like this, and our momenta are expressed in terms of P1 and P2, it's very reasonable to use here a matrix that has the mass of the first elevator and the mass of the second elevator as its two diagonal components, and 0 for the off diagonals. In other words, P1 is equal to M1 Q1 dot, and P2 is equal to M2 q2 dot. There's no communication between this velocity and this momentum, and this velocity and that momentum. So why bother with having this matrix representation? Why not just say the first degree of freedom, q1, has a certain mass that gives us a certain momentum. The second degree of freedom, q2, has a certain mass that gives us a certain momentum. Why bother with this more general representation? That's a great question. To answer that question, realize that I have a choice in how I describe the configuration of the two elevators. I'm going to give you a hint about that choice in two different ways. First way to look at it is, right now I've been describing the height of the first elevator and then the height of the second elevator. But suppose instead that I told you the average height of both elevators. So I gave you q1 plus q2 as one of your pieces of information. That's a single real number. And the other number I gave you was the difference in their heights, q2 minus q1. If I gave you the average height for the two elevators and the difference in height for the two elevators, I'd also be giving you just two numbers. Do those two numbers give me the same information as giving you q1 and q2? What do you think? Well, I know that the average is q1 plus q2. I know that the difference is q2 minus q1. So if I have both of these equations, I can solve them for q1 and q2. In other words, from the average of two numbers and the difference of two numbers, I can figure out what those two numbers are. The reason that's important to realize is it means that instead of describing the configuration of my two elevator system in terms of the height of the first elevator and the height of the second elevator, I could equivalently describe the same system by the average height of the two elevators and then the difference in height between them. Would give me description of the same system. However, if I used average and difference, then the average height now is really talking about both elevators moving, and the difference is talking about both elevators moving. And so now when we write down the relationship between velocity and momentum, it's no longer clear that you can separate out the first variable and the second variable into two separate equations. So that's just a hint for why we leave the general representation of the mass matrix, even though for the simple examples we've been working with, it's clear that the numbers can just go on the diagonal. Now I told you I'd show you two ways of seeing this, so let me show you the other way of seeing that. Remember that for the two elevator system, we had that one of the elevators could be thought of as the x-axis, and the other elevator could be thought of as the y-axis. And so any point in here gives us information about the position of the first elevator and about the position of the second elevator. But if I have a point on the plane, are these the only set of axes that I can use to tell you where this point is located? What if instead of these axes, I used this pair of perpendicular axes? Well, if I tell you how far to go along this axis and how far to go along this axis, you can also specify any point on this plane. But what's the difference between these axes? Well, when I move along this one, q1 and q2 are both increasing. In other words, moving along this one looks very much like the average position of q1 and q2. Whereas when I move along this axis, q2 increases while q1 decreases. In other words, it looks very much like the difference between them. In other words, changing coordinates and talking about my pair of elevators, not in terms of their individual heights, but in terms of their average height and difference in height, is the same as picking different axes for talking about the position of this point in configuration space. So because any physical system can be described by different choices of coordinates, sometimes we need the generality that the relationship between the velocity and the momenta is not simply a relationship of each variable or each dimension individually, but that there can be crosstalk through these off-diagonal entries, which is why, in general, we write that the momentum is related to the velocity by some d by d matrix.